My name is Anastasia Budka, and I'm a research scientist at the Lawrence Berkeley National Laboratory. I'm very excited today to talk about how we're using the Risc-v ecosystem to build an open control stack for quantum computers. And I would like to start my talk with a short introduction about quantum computers and about how misleading is the term quantum computer. So if we look closer into some of the recent publications and some of the media announcements, we can see that most of the industry and big journals that they use quantum computers versus quantum accelerators to report their results. But what I find extremely confusing is that uh, most of those announcements are not actually about the quantum system, but about the quantum processing unit. And the problem is that a quantum computer is not a quantum processing unit. Quantum computer is a quantum processing unit that is somewhere, here on the bottom of this diagram, surrounded by a large number of different classical electronics that is designed to control those quantum chips. And this particular example shows us superconducting technology where the quantum chip is located in the so-called dilution refrigerator that is controlled by different kind of waves that are coming from the upper level on the stack. So I would like to use this to illustrate and emphasize that in order to use the terminology correctly, we are designing the quantum system and the quantum computer that is including all of the control electronics. So that being said, I would like to continue with some of the abstraction levels and the main concepts in quantum computing. So on the top of our abstraction level stack, we have quantum computation model and quantum algorithms. So those two levels have been an active area of study long before any physical implementation of quantum computers became available. So, and even the fact that the recent research and development bring the awareness of hardware to the high levels, specifically for so-called NISQ applications. NISQ stand for Noisy Intermediate Scale Quantum, but it's still very important to understand that abstraction and modularity are crucial for scalability. So we would like to emphasize that those levels are hardware agnostic. Then on the bottom of this stack, we have low-level control and quantum chip. So both of those levels, they operate at the level of physical pulses and have very limited or no notion about the software whatsoever. They don't know what kind of algorithm is run or what kind of computation model is used. So those two separate levels of the stack, they are connected by the intermediate levels that are depicted here in general as quantum gate sets, quantum circuits, and the quantum control unit. And those levels are both hardware and software aware because they are designed to bridge the gap in between the theory and practice. And in our research in the lab and our work in designing the quantum testbed, we focus on those three levels, how they intervene with each other and how they affect the efficiency and the potentially scalable future quantum computers. So I will go and continue to talk about the system architecture in more details and how is it done today and why it's not going to work in the future. So there are two approaches in general to control the low level of the quantum stack. The first approach is so-called software implementation, where you have most of the control that is done by the software at the level of the user machine. Here on the left, the blue boxes depict algorithm circuit and a sequence of pulses that are implemented in software at the user level machine. And then those sequence of pulses can be offloaded through some sort of interface to the low-level control. And the low-level control does not have any intelligence, or very limited intelligence, to make any decisions. So this software control approach is something that's being used now, and it does have some advantages. It is clearly more efficient because you have everything in one place, right? You have all of your pieces that are located in your machine. It is easier to implement and modify because it's software, and it's been pretty suitable for the Risc experiments, because Risc experiments are not that big in terms of the size of the quantum chip right now. So, but it does have the disadvantages, especially if we look into some future implementations. So here, if we look closer, we can see that there are two types of latencies in the system. The first type is something in between the host machine and the classical low-level control that could be an FPGA. So it does take time to offload those sequences of pulses or some sort of commands down there to be executed. And then we have a second latency, which is to generate the pulse that is coming from the analog level down to the fridge. And it does have a limited bandwidth, obviously, because to offload those pulses. And given all that, it seems like it will be having, we will have trouble to scale this system if we have a larger number of qubits. And clearly, it does also have a limited flexibility because we don't have any actual intelligence closer to the fridge. A second approach is a hardware implementation. So compared to the previous one, we do bring a processor, a control processor, closer to the low-level control. It can actually sit on a single FPGA, and in such a way, we bring these smart ideas closer to the edge. This is not a new idea. This is something that in some research called edge computing. In edge can be actually anything, not only the quantum chip. It can be something big, like a big facility that we have at the lab, like ALS or something else. So so the idea is that you give more control to hardware, and at the user level, at their machine, you have an algorithm that is expressed as a quantum circuit, and then it is compiled in some sort of the quantum assembly language that then can be executed on the quantum control processor. So in such a way, the advantages of this approach is that it allows us to reduce the latency, right? Because we don't have that latency, that offloading latency anymore. That allows us to build so-called fast feedback when a decision has to be made quickly based on some sort of the measurement that is coming from the fridge. It does have an extended functionality in place. It does have a better potential for scalability, and it is going to be more suitable for the experiments beyond Risc era. So all of those advantages come together with the disadvantages, and among them, first, that can require and may require the specialized solution because the quantum computation is very special, and just the general purpose processor will probably not work efficiently for the specific needs of the quantum computer. And it is obviously harder to implement and modify something when it's done in hardware instead of it's done in software, where you have just your Python function that calculates something for you, and then in a half of an hour you have your experiment running. But all of a sudden you have to modify an RTL for that, right? So if someone is not willing, dealing with those two challenges, another solution would be to use a commercial solution. And then a commercial solution that start to appear right now. We have Zurich Instruments, we have Keysight, and some other companies that start to develop those specialized quantum control units, but that requires the commercial support. That means that they will probably provide us some kind of cloud access or some APIs, and that's it. The stack is not going to be transparent. And unfortunately, at this stage of the quantum computer development, this approach is not yet something that will work, because we believe that a lot of the questions have not been answered yet in terms of what are the needs of the architecture for this sort of computation. And for that, we need to engage the community, we need to engage the research, and for that, we need an open stack. We need the transparency. So and later in this talk, I will be talking about how do we address those two challenges instead of going into the commercial solution. How do we design those special purpose quantum processors using Risc-v and Risc-v ecosystem? So those two challenges we address with the Risc-v. And as you know, the Risc-v is an ISA that has been designed as modular, open source. It has a very active community and a very rich ecosystem. So we did design a quantum instruction set architecture extension that we call Quasar. That is an extension that supports quantum operations, some timing control, and some additional operations that are very crucial for efficient execution of the circuits. Then we designed it to be transparent, adaptable, and open. And in order to address the challenge of that being hard to implement and modify, we would like to use, and we are using, novel technology in hardware design and development, such as, for example, Chisel language. As you know, Chisel's been used for rocket chip generators, some other generators that are more modular and parameterizable. So those two challenges are addressed in this way. And right now I'm gonna switch and talk exactly about what we've done with Risc-v for quantum. And we consider in our research and in our development two different approaches. So the first approach of the Quasar extension is to design it as a greenfield extension. And if you know what the greenfield means, it means that that extension is something that can potentially lead to some conflicts with other extensions. And the reason we did it because we actually wanted to have a large number of opcodes to cover a large number of gates, of quantum gates. And for that, we had to sacrifice some of the extensions. So in the right, you can see the figure of an implementation of this Quasar instruction set in the form of an, we call it I-score. So an I-score is more like an educational and research core that is based on the Sodor core, which is a 5-stage in order processor with some green boxes that indicates how the processor has been modified in order to support the quantum functionality, such as TSR, which is a timing special purpose register. Then we have an MSR, which is a measurement status register, some additional blocks here and there, and then also the quantum interface block. So this approach is it's been very interesting. It has a very highly customized, and those blocks are very tightly integrated within the processor microarchitecture. So the second approach that we've been recently working on is to adopt Quasar within a so-called ROC processor instruction format. So it does allow us to use already existing software support, because in case of and on the previous case, we had to modify the compiler to support our extension. With ROC processor, we already have this support in the compiler. We already have this support in the operating system. So on the right figure, in terms of the architecture, you can see that those green boxes, they have been moved to the coprocessor. So it's more isolated and even more modular. And the Risc-v rocket core it remains untouched, and we're working on the Quasar coprocessor. But it obviously has a little bit lower level of customization and flexibility, because we need to adapt it to support the ROC format. So I'm not going to talk more about the first approach. We actually have a full publication that's presented in the International Conference of Rebooting Computing. And in this research study, we have evaluated our quantum instruction set architecture. We actually designed metrics and methodology to be able to evaluate the efficiency of the encoding. We also compared it to some other existing solutions, and we projected the scalability and performance for our implementation. So I would like to refer you to this publication, and if you're interested in this topic. So I would like to talk about the second approach, because this is something that's been made, implemented, and is actually running as a system. So we use the Freedom platform that is available and being done by Sci5 to actually run our control system on the Xilinx FPGA. So it has three components. The first component is, as you know, it's like a Risc-v, and untouched, not modified, regular core that run full Linux, and it has a remote communication with the host user machine. Then through the ROC interface, we are using the extended instruction set and Quasar coprocessor that does have all the additional functionalities to talk to the analog backend. So it has some sort of the pulse library. It has some additional functionality for calibration and readout post-processing. And in the end, we have a custom designed cubic analog backend that actually generates the pulses that are coming from the FPGA and the board. And it does some phase manipulation, does fast readout, and it does some timing, very tiny timing control. So, and all of this system is working, and it does generate the pulses. And in addition to hardware implementation that is running on the FPGA, we also have a full software stack that is working right now. That is coming from the high-level circuit description to the actual executable. So here on the bottom, if you're not familiar how the quantum circuits are visualized, so this is how the quantum algorithm is depicted. So we have several qubits, and then we have different gates that are applied on different qubits at a certain time. And this circuit is composed of so-called high-level logical gates that needs to be then transformed and decomposed down to so-called native gate set. Native gate set is different for each quantum chip implementation, because not of the all theoretical gates can be actually transformed into a form of microwave. So the gate needs to be decomposed down to this native gate set that is supported by the hardware. So we have our compilers and our translators that do this. And then we have our Quasar library that takes the quantum assembly quasm they call, and transform it into an executable together with the assembly for the rock instructions. And at the end, we have actually the pulses that are coming out, and those are the example of the pulses that we've been able to generate with our stack coming from the high level to low level. And yeah, so that's this is what we are doing now. So just to conclude my talk, this is not all that we're working on. We have much more future work to do. We are very curious to see how scalable the solution that we have. We are very curious to see about how we can use the cool technologies, for example, superconducting, that will actually change a lot the microarchitecture if we decide to implement it in a different technology. And there is much more to this. If you are interested, I will gladly answer your question. So Advanced Quantum Testbed is a big project at the Lawrence Berkeley National Lab. We have a lot of people working together. We have industry that is helping us. We have people who design the delusion fridges or integrate 3D integrated quantum processors, and obviously the intermediate levels that I talked about today. And I would like to thank you for your attention and take any questions. So all of our work is done to be open source. So please feel free to reach to me if you're interested in the quantum instruction set extension or our hardware implementation.